So far in quantum mechanics, we've been working with definite quantum mechanical states of one kind or another. These have been wave functions, or perhaps spinors, or some other vector in an appropriate Hilbert space. The physical world around us is, however, complicated. Certainly too complicated for us to model it completely. How are we going to deal with this in quantum mechanics? To handle complicated situations in the classical worldview, we use the ideas of statistical mechanics. If we're looking at something like a gas of atoms or molecules, we can take a statistical approach, assigning probabilities that the classical system is in some specific kind of state. For example, if we divided a box of gas atoms into two parts, we could come up with some probability distribution for the numbers of atoms in the two different sides. Often, we can simplify our view of what happens to a specific physical object interacting with a complex world by such a statistical approach. For example, if we were looking at the pressure of the gas on a wall, we could base that on a statistical average from the different gas atoms bouncing off the wall. In quantum mechanics, can we somehow come up with a similar statistical approach, useful at least in some situations for describing a quantum mechanical system interacting with some complicated environment of some kind? One specific example problem we would like to understand is how to model optical absorption in atoms more realistically. Our simplest model gave us atomic absorption lines that are infinitely sharp, mathematical delta functions. If we find the correct statistical way of having those atoms interact with the rest of the world around them, perhaps we can have a more realistic model and also get rid of those unphysical delta function lines. In fact, there is quite a useful way of looking at such interactions of quantum systems with a complicated world. One that enables us essentially to take a conventional statistical view of that interaction, yet still retain key quantum mechanical ideas. That approach is to use what is called the density matrix. This is a way of rewriting quantum mechanics that can be entirely consistent with everything we've done so far, but that can also connect to conventional ideas of probability. Incidentally, because it can handle both the quantum mechanics we've done so far and also incorporate these statistical ideas, it's not uncommon to see quantum mechanics written down in this notation, even if the statistical ideas are not particularly important in a given problem. So, in addition to being quite useful in extending what we can do, it's also a notation that we need to be able to recognize and understand. So let's see how we set up this different way of writing quantum mechanics and how we can make use of it.